The student is able to apply mathematical reasoning to create a description of the internal potential energy of a system from a description or diagram of the objects and interactions in that system. A small object oscillates back and forth at the bottom of a frictionless hemispherical bowl, as the drawing illustrates. The radius of the bowl is r, and the angle theta is small enough that the object oscillates in simple harmonic motion. Derive an expression for the angular frequency omega of the motion. Express your answer in terms of r and g, the magnitude of acceleration due to gravity. At point 1, the block has gravitational potential energy because it is at a height compared to point 2. At point 2, this gravitational potential energy is converted to kinetic energy because it gains velocity at point 2. We can find the height of the block at point 1 by subtracting r cosine theta from r, because r cosine theta is a component of r that is perpendicular to the horizontal. The problem states that the object oscillates in simple harmonic motion. This means that the motion of the block is similar to the motion of a block in a circle, if we could only see the x component of the velocity. At the bottom of the circle, you can see that the tangential velocity is equal to the x component of the velocity. Tangential velocity is equal to omega times r. This means that if we know what the tangential velocity is, we can find omega by dividing by the radius. According to the law of conservation of energy, we know that the total energy at point 1 has to be equal to the total energy of the system at point 2. Since the object is at a height at point 1, the energy of the system is stored as potential energy, and at point 2, that potential energy is converted to kinetic energy. Previously, we found h in terms of r, and we can substitute h for r minus r cosine theta. Finally, by dividing both sides by m, multiplying by 2, and taking the square root of both sides, we can find the maximum velocity. We know that omega is equal to the maximum velocity over the radius, and now we can substitute our expressions into this equation and find the final answer, which is square root of 2gr times 1 minus cosine theta all over r.